I am so excited to be here today, kicking off what is going to be a fantastic week. So what I want to do today is tell you a story of a language, and like every good story, it involves a problem or multiple problems, so there's some kind of dilemma. My problem is that I increasingly use web applications for everything, bug tracking, project management, even version control. But I don't use it for things like code editing because my code editor is completely tricked out to be exactly the way I want it. If it doesn't do something that I want, someone else has written some type of plugin for it or extension, or I've written one myself. I can't do that with web applications, not yet. The other problem that I have is that I make web applications. So our company makes these big process and workflow heavy web applications that regular people use to get their day jobs done, which invariably means they're doing things that nobody ever anticipated they would do, and they have to do this in fairly cumbersome ways. It'd be great if they could extend those applications or sufficiently clever user code and then share those extensions with other users within the context of that application, so there's kind of an ecosystem of extensions for your web application. This would be fantastic. How do we do that? Well, we're going to need some way for people to express functionality, and that means a language. I'm an application developer, so I mean, what do I know from developing languages, right? I know nothing. So let's do this the simplest way that we can. Let's use JavaScript. We'll just give all of our users access to JavaScript, and they can code whatever they want. And this is a great idea for a few milliseconds until you remember that even if there was a way to prevent your application from devolving into some fetid swamp of attacks through various vectors on other applications, you still have the problem where users can write extensions that do things accidentally, like delete all of their data if there's a bug in the code, right? You really don't want that, so you need this granularity of control. But you can't really get that in JavaScript. It's too mutable, there's too much surface area, the language is too big. So we're going to need a smaller language. Insert appropriate boat-shaped meme here. So what would that look like if we had it? We would need to be able to create and edit templates, since we're working on the web, specifically HTML, but they could be anything. We need to be able to extend the functionality that the application presents to us. Ideally, it's presenting this in a way that is fairly atomic and orthogonal, so we can take these primitives and compose them in various ways. And unfortunately, we're also going to need to be able to express interaction between ideally modular components that are making up our UI, because we need actual real functioning GUIs, which is essentially simulation programming and everything that entails. Okay. So let's look at each of these just briefly to see what kind of attributes we need from these three different languages that we apparently need. One is that we need to be able to embed some code in some strings. At the very least, we want to embed variable names because we don't want to deal with C-style printf statements over long, long strings. That gets untenable. We can quibble about how much logic we put in. There's a big move toward logicless templating programming, and there's a big move away from that now. That seems to vary based on your organization. In my case, my designers are code compatible, so I give them huge amounts of expressive power, and they use it to do amazing things. But regardless of our take on how much logic should go in there, we can definitely agree that we want our template code to be side effect free. You don't want side effects in your templates. That's a bad idea. So we also need a way to compose these things. I was going to give you a really well-reasoned argument that we should make this a dataflow language. Then I realized that there is actually no way to argue that in a well-reasoned way. So I'm just going to express my preference for having this be a dataflow language. It makes a lot of sense to me because on the server side, when you're getting a request in and we want the code to run on the server side as well, you're essentially just doing a data transformation over something, right? You get some input, you do a data transformation, maybe there's a round trip to the database, you do some more data transformation, and you send it back. Regardless of whether it's a query or a command, this is what that pathway looks like. On the client side, it's a little more arguable. We could have any type of language here. I like dataflow languages, partially because they maximize the legibility. So actually, as the first talk was saying, the way that we tend to read naturally is you take some input, you do something with it, you do something with it. The way that we tend to write functions is you've got G that calls F, that calls X, right? So if you're doing function composition, or if you're doing, G of F of X, or O of X, or whatever, you always end up with the X at the end, and it's kind of backwards. So if we can do this in a stack-based way or a data flow way, we get our X coming in, and it feels like a more natural read. That would be nice, because these are going to be read a lot. We also need a language for coordinating things. So ideally, this would be modular. It would be reactive, whatever that means to you. So to me, that means we're going to be connecting to things from the outside. Those will trigger some cascade of events, and then pass things off to the outside again. In particular, though, we want this to be limited because we don't want our coordination between different components to be affected by the logic in those components. We want to be able to reason about these things at two different levels. So we'd like to be able to look at how things are connected and make reasoning about that, and then look at what those things actually do and reason about that separately. So we want this separate from the logic of our program. So here's an idea. Let's put them all together, except that doesn't work because I just said we want our coordination to be separate from our logic. So here's a new idea. Let's put a couple of them together. We'll try to stick those first two together so we minimize the number of new languages we have to create to solve this problem. This slide is hard to read, but fortunately the code is not very hard to read. So you have subject, verb, object, and I tend to think of this as math, for example, as being some entity that is responsible for everything mathematical in nature, and I'm giving him a command. I want him to add some things, and those things are a couple of values. Some of you are wincing because adding two values takes 20 characters. It's highly readable, but not highly typable. So maybe we can do a little bit better. So we're just going to alias the words math, add, and value as the word add, and essentially just drop those in and replace it. You can see that here. So we've got pipes. In this case, we're piping 3 into add as one of its values. We're adding those together, we get 8. We've got pipeline connectors, so we want to be able to take a value from one place in the pipeline and use it multiple other places in the pipeline. This is the syntax for doing that. It means that the wiring in our pipelines, instead of being linear, looks like a directed acyclic graph, which is useful. Anything that starts with an underscore is effectively a static single assignment variable, but they're not actually variables, so maybe a better word would be good. We want to embed things, so we have to wrap them in some way. We're wrapping them in curly braces. It's nice and cozy and comfortable. Right, I thought I would have to defend this a little more, wrapping everything in curly braces, but in this crowd, a lot of you have a Lispy background, so you're comfortable with wrapping things. The thing that I do have to defend a little bit is using lambdas that look like strings, which is horrible. But I used to sweat over details like this a lot, and then I changed the way the engine worked so that I just compile everything down to this kind of virtual machine language, and I have a virtual machine that runs on top of the JavaScript virtual machine, which runs on top of other things. And so I'm miles away from the metal. I'm in this very rare air up here. But that means that I don't actually have to sweat the syntax, because you can compile down to that same virtual machine language and have syntax that makes you happy. Here's an example of string-like lambdas. So we're just mapping those double underscores at the beginning mean take whatever the process input is to this pipeline. Double underscores later in the pipeline mean take whatever the last segment was, so what came before the pipe. We don't usually have to use those because we get the implicit piping through the pipeline into the command, as we've already seen. But occasionally you want to use that multiple times or places in a command. Named parameters, I don't know if I mentioned that explicitly, and order doesn't matter. So this will actually do exactly what you think it will do, which is to say that if we go to daimio.org, which is up as of yesterday, and we do this, we get what we would probably assume we would get. Okay. So the question you're all asking, can we do cellular automata? The answer is, this is almost the hello world for programming languages in some ways. The answer is yes, we can do that. This is a 3-state excitable media simulation, and it doesn't have any, so it's 3-state, but it doesn't have any state in the sense that we're not accessing stored state. This is just kind of traveling through the pipes, and we're not saving it anywhere. So it comes in here from somewhere magical that I'll explain later. And it's essentially a list of lists of numbers. We're going to map over that. Note that we're explicitly passing in the scope that we need inside of this. And every time we go down a layer, we have to explicitly pass that scope in. Certain things get injected into that scope by the commands that we're using. So in this case, map is going to, in addition to giving us a process input that we'll use here to read through one single list inside our list of lists, so one row effectively, it's also going to give us underscore key and underscore value, and we get underscore cells from this with statement here that brings in cells, and this is another label for the process input. This little guy looks like a primitive that gives you a hash. It's actually just an alias, like add for math add value. There aren't actually any primitives in here, so all of the functionality is at the same level as any user level commands that your application publishes into the language. So once we get down inside a particular row, we're just going to switch over that. And this little bit here is going to take three columns out, then take three rows out rather, and then take three columns out. So it's going to give us in the end a list of 9 elements. We'll take the max of those. If that's equal to 2, then we want to activate and go to 2. Otherwise, we'll just stay at 0. So this is the 0 state. It's excitable. The other states just kind of fall off, and this is sort of a refractory state that doesn't get excited. This is our excited state that falls to that refractory state. So that's a little bit confusing. Maybe we can actually just look at an example and see how this works. So we can start this up, and we can edit the code here, and it will just kind of live edit that, which is nice. And that's horrible, so let's not do that. Okay, that's better. So we've turned the speed up, and now I'm not going to be able to get this started, am I? Because it's, oh, good, okay. So this is just modulating through 3 states. This is a 5-state excitable media, and now we've got all 5 states showing. Okay. So this is what the code looks like. The part that I wanted to focus on was right here, so we can actually see this in process. This is a 5-state one. As you can see, there's a couple of extra states. And also, it's stateful in the sense that we're actually storing this state somewhere. But we'll leave somewhere slightly unspecified for now. Okay. Okay. Right. So how do we express interactions? We saw a little bit of that just now, but I want to back up and pretend that you didn't actually see any of that code that you saw. We need a language that gives us coordination between ideally modular components. There are a lot of ways to do this. So there's some process calculi here that have formal algebras for kind of operating over the formal languages that you use to describe these connections of processes. And then there's other models that don't necessarily have a formal algebra for doing this, so you don't get as much leverage in showing equivalence between 2 networks. But in actual practice, these can work quite well. Is there anything in particular I wanted to tell you about these? So, funny story about the Blackboard model. No, we'll save that for later. Expediency, above all else. These process calculi and friends vary over a large number of dimensions. Those aren't necessarily orthogonal, so it's hard to draw a chart or something of this. I will undertake that someday. But we can look at a couple of the dimensions that they vary over and talk about which one we should choose based on how these dimensions affect our problem and our desired goals. So mutability of network, that first one, that just means how is the network capable of changing over time? So for example, in early CSP, as it was first formulated, I believe, you couldn't pass channel information along channels, which meant that your network was fixed at runtime. This gives you a lot of reasonability about your network because you can think about how data flows through the network over time and also how any components will change in state in response to that without also having to think about how the network changes over time, which really complicates out reasoning. Unfortunately, if your process network is distributed across a real network, that real network is going to have partitions and you need to respond to that. So you really do want to be able to pass information along channels, in this case, or addresses between actors or whatever your your process for doing this is, and extend your network at runtime and adapt it. So it's reasonability versus the ability to respond to events on your network. We're going to choose reasonability, and that means that we're putting all of these on one single machine. We can do that, though, because our goal is to build GUIs. So we get lots of reasonability out of our fixed network, which is great. And then these other dimensions have similar thought processes along them. And what we end up with is we want to keep it local on one machine. That allows us to keep it fixed. That allows us to reason about the network. We're going to have unbuffered channels and direct communication between things. And there's lots of interesting things that fall out of this, but the end result is that we kind of have to make our own up. So we're going to have something that takes from the established work, but uses it in a slightly different way, because there isn't anything that has the characteristics that we want. We need some safety. So let's use these components that we're using to model our GUI and our simulations and our games as execution spaces for the language, and attach a dialect that contains a list of commands or functions. I call them commands. And then in that execution space, that bit of code can only make use of the functions that it's provided by that execution space. We also need a place to store state. Obviously, we're going to put that in our execution spaces, but spaces are hierarchical, so they're nested inside each other. And so there's a question of whether you can share, or whether you have to share state between them. You really don't want to, and once you do the math, it turns out you don't have to, which is great. So that's nice. Where does the code live? So I've said that we're executing code inside these spaces, and we can inject that in, I guess, and run it, or we can have a space that has some code in it that we execute. But we end up with a lot of problems in coordination at that point, because you might need multiple bits of code that run at different times based on different input ports. And how do you coordinate all of this? So what we're actually going to do is take our code and wrap it in a thin wrapper that we'll call a station, and then we'll connect the station to other spaces that are children of the big space that we're in. And this would be better if I could show you a picture, but the prototype GUI is not quite up to screenshot level yet. And then we'll link those stations, which contain code, with the spaces that contain whatever they contain, and have a routing network that goes over all of this. It makes more sense when you see it in practice. How do we avoid side effects? So we'll push all of the side effects. Everything that connects to the outside world will be a port from the outermost space that we're implementing. And this brings up the problem of how do you, for example, make a query to the database from a bit of code. So we have a different way of routing those synchronous calls than we have from routing these asynchronous calls, which I guess I can show you instead of telling you about. So, oh, we're still going over here. That's okay. So let's make a sequence. So the idea here is we're just going to generate the sequence of positive integers. So we just start adding numbers. And how does this work? This is just some window dressing. We're going to call our Daimio runtime. Down here, we're going to set it up, build a new space. That's our outer space, great. And then we've got a little bit of HTML. We're going to grab onto this ID, add one, and in particular, we'll make a port here that grabs onto it on submit and brings a value into our space. So now we can work with that. We'll route that into an anonymous station that does some stuff. So it takes the last value from the sequence that we're storing as state on this space, adds one to it, pokes it, which is just going to push that onto the end of the sequence because we don't actually tell it where to poke, and then we'll store that again. And we'll trigger this thing called changed by sending a message to it, and that's just going to be a kind of a channel type thing that we can push things into. All it does is pass along the value. We'll pick that up down here, grab our sequence, join over it, and push that into our div here. So this is what that looks like. It'd be nice if we could do something a little more interesting. Instead of just a sequence of positive integers, what if we wanted a sequence of odds or evens or count by 10? So here we can do that. We can take some number and add that number in. This looks very, very similar. This is just the diffs in the code. We'll just have another form. It has an input called value. Down here, we're going to link to that. So we get a message in, and pull out the value, add that to the last item of the list, and then call this saver thing by pushing a message to it. And that's just going to do exactly what we did, but in a modular way that we can also call from here. Okay. Any questions at this point? I'm going fast through some things and slow through others. Yes, I'm sorry, I meant to do that. You're all squinting. Yeah, so this language out here that is not wrapped in these braces is fairly new and subject to change. So I might find ways to pretty that up in the future. And ideally, you'd be editing the code, but also looking at the graph. So because this compiles down to a virtual machine language, we can, in theory, project that compilation up into both the code that you're seeing and also a graph that represents it that you can actually edit. So you can edit either side, and the other side edits itself correspondingly. That's kind of a hard problem, so I haven't solved that yet. But it's an interesting feature that you can potentially get out of this. Okay. So what we really want to do is have any sequence at all that we can imagine. And so we'd like to execute code. And we can do that. So this is obviously the Fibonacci sequence. We're reaching into our sequence, which is being passed in here. We're unquoting this to compile it, and then we're executing it with context. And we're just taking the last value and the second to the last value and adding those together. And then if those are 0, as they are when we start, we're making them 1. So that gives us our bootstrapping here. This is great, we can execute code, but there's a problem because we can also do something like this and modify our sequence. We don't want to do that. We want to kind of force people to just add another item on the end of the sequence and not have access to the entire sequence itself. So that looks like this. This allows us to keep our sequence safe. So we'll add a few things to it, and we'll try that trick again. And now we can't actually modify this sequence value. In fact, we're not really doing anything at all there because we're in a different space altogether. So this is a new space that we're embedding inside our outer space. And we're just setting up an import and an outport. The name is doubling as the port flavor. And then we've got exactly the same code that we had before. But it's inside this other space. And we're just doing a little bit of routing inside that space to get it into the station and doing routing on the way out. So that's great. This is what that looks like all together, I think. Right, good. So that's just a Unicode histogram of the sequence to date. This is the famous Collat sequence. And I've set up a little more code here, not there, here, that allows us to map the Collat sequence over this. The conjecture is that any number you start with eventually gets to the 1, 2, 4 loop. And we can see that that is in fact happening here. Okay, nice. So, so we've shown that we can take code and execute it and be safe about that in some sense where we're not sharing state between things. But what we'd really like to see is a more grandiose example. And unfortunately, I'm going to have a hard time doing that because I can't connect to the network. If you can connect to the network, you can go to daimio.org/8000, and that will get you into a turtle simulator. And then you can tell your turtle to move forward and turn. And if I was connected to the network, we would potentially see people doing that here. So the idea is that we're passing code from machine to machine and executing that code on each other's machines, but that code only has control over your own turtle on other people's machines. So let me see if I can do something local that will at least give you the flavor of this, even if it's not. Daimio.org. So, oh, that's local also. daimio.org/8000. So there's just a little node app running under the server there. So I can click one of these, in theory, and the code shows up over here, and then I can send that, and my turtle does fancy maneuvers for me of various kinds. And ideally, at least some people are seeing this on their machines in a group setting, but since I can't connect, I don't know if it's actually working or not. Yeah, so I'm really excited about the potential that this has for making programmable applications, and in addition for sharing code in particular ways. So, another problem that happens is maybe you make a game or something, and maybe that game has an element where people are kind of building out the game world. So Glitch is an example of this. And the problem is that the more people who play your game, the more tax there is on the server and the more money it costs to keep all the servers running, which means that if you can't monetize your game or your tool or your product or whatever you're making really quickly, it's going to go away, and everybody loses all the work that they've put into it. What if we could flip that on its head so that the more people who use it, the more power you have, because you're doing the execution on the client machines and people are actually saving that state on their machines and passing code around. So this is what I want to get to ultimately, and I'm very excited about that idea. These are steps in that direction. Do I have time for questions?